All right, thank you for the introduction. Thank you all for being here, and welcome to Debugging Code That Crashes the Beam. So let's just go over the general layout. I'm going to introduce the main ways that Erlang interfaces with C code, though that landscape might now change because people are investigating other languages which compile object files. And I'm going to talk about when things go wrong. And that will then segue into Debug VMs and ETP, the emulator toolbox for pathologists. I'm going to show some very, very small, completely contrived demos that will sort of demonstrate how easy it is to take down the VM when you're writing C code. And then we're going to wrap everything up. So a little bit about me. Most of it was already covered, but I'm working full-time and I'm studying full-time. And in just last summer, my professional career as a programmer started, so I'm still very much learning about everything. The main languages that I use are Erlang, C, and a bit of Bash for plumbing reasons. Effectively, because of the really, really tight latency constraints we have in ad tech, when Erlang doesn't do something that we want fast enough, we often wind up rewriting the stuff we need in C and then usually linking it in as a port driver or a NIF. As to why I'm giving this talk, right, not an extremely experienced programmer, but there are some very cool things that I have found with respect to debugging code that gets linked into and then run by the beam. These neat things are not exactly the most searchable online. I'm hoping that this presentation will sort of serve as a signpost to help others in the future and to help you who are here. So let's dive into this. Erlang has several different ways of interacting with code written in other languages. These are the main four. There are also things like JInterface and BIFs, but I'm really only going to be talking about these three, and I'm not even going to go into very much detail. There's a really nice tutorial about that. So Erlang lets us interface with other programs, and this is really spectacular for when we need speed that the Erlang virtual machine doesn't necessarily provide, if we need to quickly encode a string differently, or if we have some number crunching that we need to do, or random number generation, crypto, or when we need to integrate with other libraries. Suppose we're using some fancy new message broker system, and that's written in C. Erlang gives you the opportunity to use that. It's completely available to you. So starting with ports, these are the main mechanism by which the Erlang VM communicates with the outside world. Effectively, a process will open a port to another process, and they communicate with each other via standard in and standard out. And already this gives us a lot of flexibility because things like GNU-plot or R can communicate through these channels. So right off the bat, we have wonderful integration with other well-behaved programs. And so the cool thing here is that the non-Erlang code is separate from the beam. It's a different process. We like process isolation here. And unfortunately, there is a bit of an introduced cost with overhead for serializing and deserializing. Next up, we have port drivers. And this is basically a port slapped onto what is called a linked-in driver. And this is basically a compiled shared object file which gets loaded into the beam. And then these callbacks are called when certain events occur. This is how the Erlang VM does file I/O. This is how it manages sockets. It also uses it in a whole bunch of different places. And so there's a really large API that we can use. We have great things that we can do with these port drivers. However, They are tricky to debug, and a misbehaving driver can cause the entire virtual machine to misbehave. In summary, they're really great for these asynchronous operations that we need to do. So any kind of I/O, port drivers are great. Lucas got me very excited this morning when he announced enif select, because, well, let's talk about what nifs are. So nifs are similarly a compiled object file that gets loaded in to the Erlang virtual machine. But the way that nifs work is that when they're loaded in, they will replace functions inside of a module with the native versions. NIF stands for Native Implemented Function. And this is how the Erlang standard library deals with regular expressions and its crypto module. When you look through, let's say, crypto.erl, what you will see is a lot of these functions will have a small macro called nif stub. And when that gets expanded, that's really an error, because when the crypto module is loaded, what should happen is that the nif library gets loaded in, and all of those stubs are replaced by functions written in C. So these nifs have really, really low overhead, which is really great because we're trying to eliminate overhead with our very, very low latency requirements. However, much like port drivers, these are very tricky to debug, and when they misbehave, they have cascading effects. These are best used for synchronous operations that terminate very quickly, and the sort of canonical definition of very quickly is under 1 millisecond. If you have nifs and port drivers that take longer than a millisecond to execute, you have sort of a responsibility to chunk up the work and to make your port drivers and nifs yield. So I said misbehave a lot. I sort of alluded to what that means. But let's just talk about how the Erlang VM schedules processes. So Erlang uses what's known as preemptive scheduling. It will start running a particular process, and after it does a certain amount of work, it's going to swap it out with a different process. It counts these reductions, which is basically, it amounts to a function call, and that measures how much work the process performs. So when a process reaches the reduction limit, it's switched out and replaced with another process in the queue. And the problem here is that the beam cannot count reductions that happen outside of Erlang code. If you have a nif that takes 5 seconds to run, it really only shows as one reduction to the virtual machine. And this is bad news because Erlang has one scheduler thread per CPU core, but these scheduler threads are talking to each other constantly. There are various synchronization processes that happen so that all of the schedulers are kind of working together, they're communicating. And so when a process is executing native code, it's not communicating with these other schedulers. And the longer that goes on, the more the other schedulers start to misbehave because it's missing all of these synchronization barriers. So other schedulers will wind up waiting on the scheduler that is running a long nif or port driver. So some general tips for writing nifs and port drivers. You should make sure that they run very fast, time them constantly. And if they do take longer than a millisecond, you should make them yield and have them reschedule themselves so that they can be executed after the scheduler has run some other processes first. And another option that is available to us is if you're writing a port driver, there is a separate thread pool, which is mainly used for for blocking I/O. You can take your port driver out and it gets put into a separate thread pool because it's probably writing to disk or waiting for a file descriptor. And you can also use dirty nifs. And a dirty nif is effectively when you annotate a nif saying, hey, this is CPU bound, or hey, this is IO bound, and the Erlang VM will basically use dirty schedulers to manage this work. I don't know why that's happening. Either way. So what do we do when we have bugs in our port drivers and NIFs? We have a really great wealth of tools for debugging C as well as for debugging Erlang. However, we can't really use any of them when we're debugging C that gets run by Erlang. We run into trouble because this has happened that the beam binaries that I use don't have debugging symbols. So if I try to use GDB and I'm printing a backtrace, I tend to get a bunch of question marks, which is not always helpful, but that's fairly straightforward to fix. Another problem is that Valgrind will occasionally report false positives saying, hey, this thing is leaking memory when it actually isn't. It just happens, I believe, because the Erlang virtual machine has its own memory allocation. And it's also difficult to run NIFs and port drivers in isolation. These NIFs and port drivers are written in such a way that they're meant to be linked in and run by Erlang. There is no sort of main function in these. So if you want an entry point so that you can do fuzzing, let's say with American Fuzzy Lop, it's really not straightforward for NIFs. However, a colleague of mine has more or less, well, he has something working. His name is Julian Squires. He presented at last year's Erlang Factory about this tool called Niffy. And effectively, it's just a very small shell that will let you load in a NIF and feed commands to it. And then Niffy, with whatever NIF you decide to load, can then be tested using AFL. It's very handy. We usually have a fuzzing job running somewhere on one of our servers at AdGear. I don't believe this problem has been solved for port drivers, really. It's a lot hairier to deal with. So the good news is that Erlang has something called Debug VMs, which is effectively just a Erlang VM binary that is compiled specially to be run in different debugging tools like GDB or Valgrind. They also have makefile targets for purify and quantify if you use rational software. And they have other targets for profiling as well. So who among you on your work machine will compile Erlang from source? OK, cool. That's a few of you. That's awesome. If you're going to be writing NIFs and port drivers, I highly recommend it, if only for the reason that you get access to these debug VMs. It is so helpful to be able to run the virtual machine with your NIF inside of GDB, and to really, it will save you weeks if you do have an issue. So I highly recommend it. As a matter of fact, in the slides, we're really just going to go through the process of building Erlang and the debug VMs. So Erlang is now in GitHub, so we clone it. And then we'll check out a particular tag. All the major, minor, and even bug fix versions are tagged, which is really sweet. And so we'll check it out. We'll read the install guide, because it's really helpful. We'll find out that we need to export this Erl-top variable. And then we're going to basically run configure, make, sudo make install our documentation. Right there, you can see that I use stow. It basically lets you manage symlinks really easily, so I can actually have multiple versions of Erlang installed, and I can swap them out pretty easily. So the next step, where we actually build the debug VMs, is we're going to go into this ERTS emulator folder, and then we're just going to make all of these targets, or just some of them. I almost exclusively use debug and Valgrind. The debug target builds your beam binary that you will run inside of GDB, and the Valgrind target will make a beam binary that can be run in Valgrind. And so once you have those, you also have this curl script, which you will invoke whenever you need to in order to start up Erlang inside of these tools. Quick note, minus RGDB will use the command line client for GDB. If you type minus GDB, it will actually run Emacs. If you like that, I just want you to be aware of it. Or if you hate it, be aware of it. So the next thing that we have is the emulator toolbox for pathologists. I find this extremely handy when I get a core dump from the beam because it crashed because I write NIFs, and I'm not very good at writing NIFs yet. So what ETP will let you do is when you're inside of GDB, you can print Erlang terms. Usually when you're in GDB, all you see are pointers to things, and you have no idea what those things actually are. With ETP, you can actually print the Erlang term inside of GDB. It blows my mind. So the source file for these GDB commands is sort of this path. I highly suggest you read it. Otherwise, you can also access the documentation inside of GDB. You just type help ETP, and it will print out some nice things for you. So I'm just going to show what I copy-pasted into my slides. So I'll start Erlang in GDB. I'm in GDB. This is an example that was taken from the mailing list. It's a really simple example that I liked. I tried to get something that I printed with IO format, but too little time. So we're going to set this breakpoint, and then we're going to run Erl. And we're in Erl. If you press Control-C, you'll actually go back into GDB, which is kind of cool. And we're just going to run Erlang nodes, bad arg. And we're going to get a breakpoint when the C function is called. And as you can see, we have these two pointers, and we have no idea what they actually mean. And so the raison d'etre of ETP is that I can say, hey, what's that thing pointing to? And it says, oh, that's a PID. That's the PID that called this function. And I can say, hey, what's that biff args thing? It seems reasonable to expect that it's the argument that we passed. And so ETP has several other really handy functions for just generally getting the state of any running process in the Erlang virtual machine. So I can type ETP process info, and I will get a message that's very similar to what you may find in the Erl crash dump file that gets generated when Erlang has to go down, but it shuts down gracefully. When you're writing NIFs, there's no guarantee that you will have a graceful shutdown. Sometimes you might just have a core dump, or sometimes not even a core dump. And so you might have to set your U limit to unlimited, then run your Erlang virtual machine, wait for it to crash, and then look at the core file. But this lets you investigate what the state of the system was when it went down. And this is really helpful when you're writing NIFs, because this is really the only help you get. If you have a NIF that does something that a normal process shouldn't do, and the operating system kills that process, i.e. your whole VM, you have no idea what happened. If you're lucky, you have a core file, and you have debugging symbols, and you know of ETP, and you can investigate what went on. So ETP has really helpful functions for dumping the memory of the heap of any process. You can dump the memory of all of your processes. You can look at message queues, and it's very helpful for when you don't have an Erl crash dump file So I highly recommend that you take a look if you decide to build debug VMs. And after that, we have just a couple of other demos. This one is borrowed by Rafał, who works in Poland at Erlang Solutions. This segfault library is basically the smallest NIF that I could find that will take down the VM basically instantly. So if we run rebar shell and we run this segfault generate function, we get a segfault. It is really good at breaking. So I've been greeted by this when working at AdGear. I have a NIF. I'm not really good at writing C, and so I will write code that crashes. And when I'm greeted by this, it was demoralizing. And my coworker Julian says, "Have you heard of Debug VMs?" And I'm like, "No." So we start up. Well, first I'll export that variable, which is important for how I invoke my debug VM. And I start my Erlang shell in GDB, and I make sure that I pass the output of rebar3 path to the code path for Erlang. I use that command a lot, and basically it will function as if I had called rebar shell, but inside of this GDB. So here I am. I get some helpful messages. Oh, GDB is loaded. I'm reading symbols from the beam binary, and ETP will print some various properties of the Erlang VM that you're running. And then you get a handy GDB prompt, and we can run this. We get our shell. I'm going to call my segfault generate again, and I'm going to get a segfault. But now GDB is telling me, hey, the operating system told you to shut down, and here is what you were running. Here is what you were running. So line 6, what is line 6? Oh, we're dereferencing some variable, and we're setting it to 100. Well, what is going on? What is the value of that variable? We'll type list, and it's null. Goodness, that's 2 lines to break the Erlang VM. It'll break any process, really, but Erlang sort of is up on, well, it's known for being extraordinarily stable. C is known for being really good at having code that has vulnerabilities in it. And so when we combine them together, we get, Erlang, well, we get the stability of the lowest common denominator here, which is C. So 2 lines takes down your entire Erlang node, but we managed to pinpoint it in a matter of minutes thanks to the Debug VM and GDB. So we're not always dealing with just segfaults. We can also have buffer overflows, memory leaks. Memory leaks are particularly troublesome because they'll just slowly develop, and then when your system runs out of memory, the operating system will kill a process, and it's fairly innocuous. So I have a very small demo, heavily inspired by that last library, which rather than segfaulting whenever you call the NIF, it'll just leak a little bit of memory. So rather than run it for days and wait for it to crash, I'll just run Erlang inside of Valgrind, and here we go. So we get a message saying, hey, we're in Valgrind, and then we get our Erlang prompt, and I'm going to say call this function 20 times. I get my tuples back, and that's it. I'm going to press Control-C, and I'm going to exit, and I'm going to see what Valgrind has to say about how the beam behaved. I leaked memory. Oh no. So I'm going to rerun this with leak check equals full, and I'm going to see what the story is. Where am I leaking memory? And so the way to do that is you're going to pass some flag, or you're going to set a variable which will basically get read in by this curl shell script, and it will pass that to Valgrind and then it'll pass what's at the end of the line there to Erl, and we're going to be back in where we were. We're going to redo everything. We're going to leak a bunch of times. And this time, Valgrind is going to say, here's your general backtrace. You called malloc from enif alloc in this function generate. And within minutes, you've sort of narrowed down where you're leaking memory to a single function, which is pretty wonderful for when you previously thought you didn't have these tools. I use this basically all the time. Sometimes one of the VMs running on our servers will crash, and sometimes if the error log information is interesting enough, I may shell into that server and build a debug VM just so that I can peek around. It's very, very helpful. I've even run our software inside of GDB, like just letting it go, and it was still surprisingly fast, which is kind of cool. But that's basically what I came here to say. I had a bit of trouble finding out about this when I was starting out, and I'm just hoping that this will sort of serve as a signpost for the future, and you will all know about it, and you can tell all your friends and when you go to the office. But basically, Erlang will let you interact with code written in other languages through the use of ports, port drivers, NIFs, C nodes, BIFs, JInterface, a whole bunch of other things. You can port drivers and NIFs are like the single easiest way to kill an Erlang node. And in my experience, they've been the most difficult thing to debug. However, we can use these debug VMs to run the beam inside of these debugging tools, and they will let us find almost exactly where we went wrong. And I make a lot of mistakes, so this is super helpful for me. And ETP, the commands for GDB, thankfully provided by the developers of OTP, provide a lot of useful commands for just generally poking around when Erlang does not quit gracefully and what you're left with is tears and a core dump. So my general one-sentence wrap-up of this is, if you have to debug a port driver or a NIF, you have help. I have some links here. The install guide tells you how to install debug VMs. You have the Erlang interoperability tutorial, which will teach you how to write ports, port drivers, NIFs, and C nodes. You have this Niffy library, which will let you run a NIF inside of a small facsimile of the beam, and that can serve as an entry point to your fuzz testing. This is not to be confused with another library called Niffy. That library is also super cool, but also super scary. The other Niffy will let you write C code inline in your Erlang source file, and then that gets stripped out and compiled into a NIF and loaded back in. It's wild. There's this Bitwise library in Steve Vinosky's GitHub, which shows a couple of demonstration NIFs that show just how the Erlang schedulers start to misbehave if you write NIFs that take too long. He also provides a slideshow, which is super handy. Going through those slides gave me a much better idea of what I was working with. And Scott Fritchie also has this NIF wait, more demonstration NIFs that show how the scheduler logic sort of degrades. And then lastly, we have a tutorial written by Rafał, who has that segfault library. And it talks about analyzing a core dump from the beam. And in it, he uses ETP to sort of show what is going on, where things are breaking. And it sort of catalogs how a particular bug was fixed. And that was a lot shorter than I was expecting, but that's all I have to say. Now go forth and debug.
Excellent talk, and bonus points for being 10 minutes ahead of time or so. So we've got time for questions and comments.
Yes, so if you have NIFs and you get set fault, what's the probability it's NIF fault? Is it 100%, 99.9?
Well, I generally think that the beam is pretty stable otherwise. So if you do get a mystery seg fault, it's probably the NIF. That's the first place I would look.
Just a question for all of you. Did that really see being seg fault without NIFs?
It can happen.
By the way, repeat the questions if you can, just for video.
If you look at, what's his name, Jim Hayden's blog, he's got a post about how to crash the beam. Gadcom.com, frog21.gadcom.
Oh, I love that blog.
Yeah. So he's got a post about how many of you crashed, and I think I made it crash.
So you mentioned early on in this, it was hard to find what you were looking for when you're trying to solve these problems. How do you feel documentation around these features could be improved?
Oh, that's a really good question. So the question was, how can the documentation around these features be improved? Well, I'm hoping that when someone Googles, oh no, my NIF is seg faulting, that somewhere Google will respond with hopefully this talk, and that this will sort of help them orient themselves. I don't really know if this stuff is not particularly documented because writing NIFs in port drivers is discouraged, or if it's just, there's so much work going on. As for things to improve it, I do plan on writing blog posts, mainly. That's usually where I find my bite-sized solutions, and if I don't find blog posts, then I'll dive into the Erlang documentation.
Do you know if ETP is compatible with time-independent debugging tools like RR?
So the question was, is ETP compatible with other debugging tools? No, I believe it's really just written for GDB. So if
I was referring to RR, which is a wrapper around GDB.
Oh, I'm not familiar with RR.
It lets you go backwards.
Cool. If RR understands GDB, or if it runs GDB in any sort of way, then I'm hoping that it could understand ETP. But that's something that would be really cool.
I think it does. I haven't tried it, but I've looked at RR to see that, and we don't use a lot of features of GDB scripting, so none of the Python interfaces, none of that, so just basic GDB scripting, and that I think is supported by RR, so it should be possible to do. I haven't done it, but it should be possible.
Okay, awesome.
That's really cool. RR for rewinding.
So what is your use case for the NIFs, and at what point did you decide it was worth the trade-off, the extra performance versus the instability risks?
Okay, great question. So the question was, what is my use case for NIFs and port drivers, and sort of at what point did it dawn upon us to sort of write these things? I unfortunately was not at AdGear at the time when a lot of the NIFs were written. However, I am actively working on a port driver which has the Erlang VM react to iNotify events. And so that's sort of the integration side. I'm really not the right person to answer that question, but I can certainly forward that.
iNotify sounds like it could be handled by a port, with an external process.
So yes, iNotify can, there is the iNotify watch or iNotify wait tool, which will sort of write something out to a shell when it does happen. However, I haven't played with it very much. I don't actually think that iNotify watch repeatedly prints events. I think it just opens a watch, collects events, and then when you send sig int to it, it'll then tell you the statistics, unless I've mistaken that with some other tool.
Well, certainly you could have just a thing that talks over a, computer socket that, you connect a port to, and so there's an external process that's running iNotify. It's just a little loop. It can crash the beam.
Yeah, it would definitely be a way to sort of isolate.
I mean, I don't see the super high throughput needed. You might get a notify event, you might get a lot of them per second, but you won't get like millions of them.
Yeah, there's definitely a bunch of different ways that you could react to iNotify events without having to write your own C code that gets loaded in and then crashes the beam repeatedly for reasons you don't understand for weeks.
Which goes back to his question of what's the real use case for writing these things.
So if you have the ability to, in this case, it's probably more for speed than for interacting with the rest of the system. So if you have a real need for speed, it's hard to avoid writing the stuff you need in native code and then loading it in. I'm, however, hopeful for the future because of Rust and the various compile time guarantees that it offers, and it builds, these native binaries. And if you write them in a certain way that Erlang understands them, you can load in a NIF that's written in Rust. And there's an Elixir library called Rustler, which does that. And a couple of my colleagues are actively investigating replacing NIFs with Rust.
Does anything stop you from doing that with Ada now?
Ada is another thing worth investigating. Light bulb.
Oh, yeah, tons of critical real-time systems are written in that, is my guess.
Amazing. I'm definitely going to play around with that.
Yeah, I mean, it's more verbose than C, but it's just as nice to program in, I would say.
I can put up with that if it's Ada. So, are there any other questions? All right. Well, thank you guys very much. I had a blast.